Hi students, here I am coming with a new video which helps you for your NEET and CET and even for JEE preparation. Notice that in the previous class we learnt about the electric field and electric field and potential of a charged conducting sphere. Now we will consider the electric field and potential of a charged non-conducting sphere. One point you have to highlight and one point you have to keep in your mind is this: in the case of charged non-conducting sphere, the charges will reside everywhere, not only on the surface, even inside. Therefore we have to consider the volume charge density, that is rho, that is Q divided by V, charge per unit volume. So we have to consider rho, the volume charge density in the case of charged non-conducting sphere. If it is charged conducting sphere, you have to consider surface charge density, that is sigma. Now notice another important point. We will take up the case 1. If a charged non-conducting sphere is considered, and if the point P is lying inside the sphere, notice that unlike in the case of conducting sphere, here the electric field intensity inside is not zero, it is having some finite value. See that the electric field intensity inside is given by the formula K. This small k represents 1 by 4 pi epsilon naught. Q represents the total charge on the sphere. Small r is the distance of the point inside from the center. Distance of the point which is inside from the center, that is the small r, and capital R divided by capital R cube, where capital R represents the radius of the sphere. So this is the formula, and this is the electric field intensity inside the charged non-conducting sphere. So here one point you have to understand is this very clearly, that is E inside is equal to K. You can write it as 1 divided by 4 pi epsilon naught, 1 divided by 4 pi epsilon naught, and Q small r divided by R cube. Now if I want to write the same equation in terms of rho, notice this one, what I am supposed to do. See this, I will divide by 3 here and multiply by 3. So here 4 by 3 pi r cube, 4 by 3 pi r cube represents the volume of the sphere, and in the numerator we have got charge. Charge divided by volume is nothing but rho. So therefore electric field intensity E inside is equal to, in the numerator I have to write rho and r divided by what remains in the denominator is 3 and epsilon naught. So rho r divided by 3 epsilon naught. So this is the equation. And another important point that you have to notice here is this: electric field intensity is directly proportional to the r. R is the distance of the point from the center of the sphere. So this is one thing. Similarly, look at the equation for the potential. Notice that the potential at any point inside, is given by this equation. Here K represents 1 by 4 pi epsilon naught, Q is the total charge on the sphere, R is the radius of the sphere, small r is the distance of the point P which is inside from the center of the sphere, and R is the radius of the sphere. Here again, if you consider the charged conducting sphere, the potential at any point inside is constant. Here it is not constant, and this equation you will get it just by integrating. See, V is equal to integration of E dot dr. If you substitute for electric field and integrate this equation, you can arrive at this equation. Just remember this equation, it is more than enough. So therefore two things you have to remember: electric field intensity inside the charged non-conducting sphere is given by rho r, small r, divided by 3 epsilon naught. where rho is the volume charge density, and the potential at any point inside is given by the equation kq into 3r square, capital R square, minus r square divided by 2r cube. That is one thing. And another thing is this: the graph of potential versus small r will be a parabola, and r is 0, small r is 0 when you go to the point, when you go to the center, this center, r becomes, the value of r becomes 0. When the value of r is 0, the electric field intensity is 0. So that means E at the center, exactly at the center is equal to 0. Not inside, I mean it is inside only, but exactly at the center only the electric field intensity is 0. And what happens to the potential at the center? Notice that you have to substitute r is equal to this small r is equal to 0. If you substitute small r is equal to 0, what happens? R square and r cube. So this r square goes, 3 by 2 r remains. So kq divided by r, 3 by 2. Look at the last equation here. This is the potential exactly at the center of the charged non-conducting sphere. So you have to remember 4 things here. 1. The electric field intensity and potential of a charged non-conducting sphere. Electric field intensity is given by inside rho r divided by 3 epsilon naught, and the potential inside is given by kq into 3r square minus small r square divided by 2r cube. The electric field intensity exactly at the center of the charged non-conducting sphere is 0, whereas the potential is equal to 3 by 2. Potential at the center of a charged non-conducting sphere is given by 3 by 2 kq by r. So that is one important thing. Now we'll move on to the next case. For a point P lying on the sphere, if the point P is lying on the sphere, now very simple, if it is lying on the sphere, this is the general equation. If it is lying on the sphere, now you have to treat that entire charges are present at the center. All the charges are present at the center. So if you treat that all the charges are present at the center, then the electric field on the surface is given by kq divided by r square, and that is nothing but rho r divided by 3 epsilon naught. And see that you are just substituting this k as 1 by 4 pi epsilon naught. Just if you want, you observe here, see that E on the surface is equal to, in the place of k, write 1 divided by 4 pi epsilon naught, and q divided by r square. Now do one thing, multiply by 3 and divide by 3, and again multiply by r, divide by r. I'll tell you why. See that now what happens? So if you just do that, yes, here electric field intensity inside is equal to, what remains in the numerator? Is q divided by r. Q divided by, can I write this as 4 by 3 pi r cube, and this r which is in the denominator goes to the numerator, and in the denominator what else remains is epsilon naught. Now this is charge divided by volume, so therefore the electric field intensity on the surface is equal to rho r divided by 3 epsilon naught. So this is the electric field intensity on the surface, and the potential on the surface as given by here, potential on the surface, that is Vs is equal to k q divided by r. You can also write it as k is 1 by 4 pi epsilon naught, q divided by r. Okay, so this also you can write it in terms of rho. So this is the electric field intensity and potential on the surface of a charged non-conducting sphere. Charged non-conducting sphere. Remember this is quite important when it comes to the competitive exams. This is not at all required for your board exams. Now one more thing. For a point P lying outside the sphere, that is not an issue at all. For a point P lying outside the sphere, see that E is equal to kq divided by small r square, where small r is the distance of the point, distance of this point from the center, So kq divided by r square, small r square, and if you replace in terms of rho, you will get rho r cube divided by 3 epsilon naught r square, and E is inversely proportional to r square in this case. Here outside and inside E is directly proportional to r, outside E is inversely proportional to r square. And when it comes to this potential, you know, the potential at any point outside is given by the formula V naught is equal to, or VO is equal to kq divided by small r, kq divided by small r. So this is the potential electric field for a point P which is lying outside the sphere, See that now in this case you can consider the entire charged non-conducting sphere, the charges to be concentrated at its center. That's it. All the charges which are distributed over the sphere can be considered to be concentrated, focused at the center. That's it. So another point to be noticed is this: the electric field and potential. Notice this: electric field and potential is same on the surface and outside, whether the sphere is conducting or non-conducting, and can be calculated assuming the whole charge is concentrated at the center of the sphere. That means whether the sphere is conducting or non-conducting, on the sphere and outside the sphere the values remain same. Only the difference is when you go inside. Inside the charged conducting sphere, electric field is 0, potential is constant. Inside the charged non-conducting sphere, electric field is given by rho r divided by 3 epsilon naught, and the potential is given by, what is that, kq 3 r square minus r square divided by 3 r square, here 3 r square minus r square divided by 2 r square kq. So I hope you remember all these formulas. You just practice these formulas, and I'll come up with few more concepts in the next session. Thank you.